All right. Happy 13.4 day, everybody. What dress of day is tomorrow? Bless you. Hip hop, right? Bless you. Yeah. All right. So we know about exponential functions. The reason we study functions in the real world is so that we can apply them to real life situations, so that we can predict. We can predict with accuracy. So we can know if something's coming. We can be ready for it. Like population growth, right? It's like, oh, we're going to need more roads. We're going to need more hospitals. We're going to need more schools because we got all these people moving in. You can predict based upon trends. So that's what we're doing in this section. We're going to create mathematical models and their word problems, essentially. So we're going to look at growth and decay models. So first of all, the exponential growth function is written in the form a times 1 plus r to the t. 1 plus r to the t. So let's look at 1 plus r for a second. 1 plus r is your base. Because previously we've seen it like this. We've seen it y equals a times b to the tth power. So 1 plus r is your base, okay? But a is going to have a special name. I'm going to label it. It says it in here. But a is your initial value, also known as the y-intercept of the graph, okay? It's like you start with like Adam and Eve. That's two people, and then it exponentially grows from there. Your starting value would be 2, Adam and Eve, right? 1 plus r is your base. Little r is called the growth rate. Little r is called the growth rate, and you can express it as a decimal or a percentage. I write that as a percent. Y'all okay with the percent symbol? Percentage? Percentage. Okay. Now the base itself is called your growth factor. The base itself is your growth factor because that's what you're multiplying by every time. Like if the base is 2 times 2 times 2 times 2 times 2, that's your growth factor. So there's two words you have to remember: growth factor, which is your base, and the growth rate, which is little r. Okay, little r is the difference from 1 or 100% to where you're trying to go. Now we do the same thing for exponential decay, except slightly different. A is still the initial value, but now we have 1 minus r as the base. And notice what's different about it? It's subtraction instead of addition, because the base has to be less than 1. So let's come back up here and say the base is going to be greater than 1 right there. And here the base has got to be between 0 and 1, just like we've already studied. Exponential decay, the base has to be less than 1. But if you find the difference between the base and the number 1, you have your growth factor, or you have your growth rate or your decay rate. So your decay rate, again, is little r, and it's as a decimal or percentage. You can do it either way. They mean the same thing. And the decay factor is your base times 0.2, times 0.2, times 0.2, over and over again. All right, I'll show you what I mean. It's probably best just to work it out in an example. So let's look at example 1. I'm going to need a calculator for this, so let me go to Minnesota. Minnesota. Standalone calculator. Ah, I know, right? Come on, load Minnesota. Minnesota's kind of sleepy on a Monday here. Okay, there we go. Oop. I think I have like 152 browsers open for Minnesota. It says Tony. Tony purchased a rare guitar in 2012 for 12 grand. Anybody know Tony? Tony must really love his guitars, doesn't he? He paid 12 grand for a guitar. If it were Gary Moore's guitar, I would probably pay 12 grand for it. He's my favorite guitarist. Do I have a favorite guitarist? Yeah, Gary Moore. Yeah. Um, my wife would probably not let me spend 12 grand on the guitar. So I would ask the people if they would take $12 instead. You're asking 12 grand, but would you take $12 for it? Hey, are you trying to lowball me? Yes. If they were smart, they would say no, right? Oh, well, you really like the guitar. I guess I can. Yeah, okay, I'll come down. $12 it is. Man, wow, how great that would be. Um, Gary Moore's guitar was actually Peter Green's guitar originally, the original founder of Fleetwood Mac. But now the lead guitarist for Metallica, Kirk Hammett, He's the guy that owns Gary Moore's guitar. So who owns Gary Moore's guitar right now? Kurt Hammett from Metallica. Not me. And he probably paid more than 12 grand for it. But this guy, Tony, my calculator's up now, so we can proceed. Tony purchased a rare guitar for 12 grand. Um, Experts estimate that its value will increase by 12% per year. Experts estimate that the value of his guitar that he purchased will increase by 12% per year. So Tony probably bought it as an investment, right? That's what you do. You buy things, you hope that the value goes up, and then later on, you either leave them to your children when you die, and they cash in, or you cash in and make a giant profit. So the question is, does this function model exponential growth or exponential decay? What do you think? Why? Why growth? You're right. It's growth. Why growth? Increase. The value is going to increase. Good. By 12% per year. It says, write the function used to model the value of the guitar. Okay. So first of all, we got to come up with some variables. Do you want to use X and Y, or do you want to make the variables more specific to what we're, bless you, doing? Like V for value instead of Y and T for time instead of X? Or do you want to use X and Y? I don't care. X and Y. You're used to X and Y. Okay. So we'll use X and Y. Not even F of X, right? So instead of using T, since y'all wanted to use X, we can use X. That's fine. But sometimes we switch it to T because time is your ultimate independent variable. But we'll use X and Y. So we'll say Y equals, and we're going to use that as a model. What's the initial value of the guitar when you purchase it? 12 grand. So 12,000. Okay. Now it's time to write the base. We have to come up with the base. 1 means 100%. 100%. Plus an additional how much percent per year? 12. Now, how do I represent 12% as a decimal? 0.12. Yeah, so I'm going to do 1 plus 0.12. So what that is, again, is if you convert both of those percentages, every year it's going to be 100% of what it was previously, plus an additional 12%. 100% plus 12%. Okay? And then y'all said to the X instead of the T. That's fine. Now, if I simplify that, that gives me Y equals 12,000 times 1.12 to the X power. I'm going to go ahead and put 1.12 in parentheses just to make it stand out from the 12,000 a little bit better. Now, you can clearly see that that's exponential growth, right? Because 1.12 is bigger than 1. There you go. So X is the number of years he's owned it. We could use T if you want. And Y is going to be the value of the guitar, which we could use F of T, or we could use V of T for value, or M of T for money, or G of T for Gary Moore of T, whatever you want. How many of you even know who Gary Moore is? Do you know Gary Moore? It's 12. It must be 10:55. All right, it's potty time, everybody. What time is it? It's potty time. Yeah. Time to potty. One at a time, though. Okay. Now, let's go ahead and answer these questions. It didn't. I don't think it asked for it, but let's go ahead and. What is the growth factor? What is the growth factor? And what is the growth rate? They're a little bit different, but they're related to each other. The growth factor is the easiest to get from the equation because what's the growth factor? I already said. What's the number that we're multiplying by each and every time for every value of X? 1.12. It's just the base, which is 1.12. That's your growth factor. Now, what's your growth rate? Yeah, either 12% or 0.12. They mean the same thing. I like to use the percentage, but you can list it as 0.12. People will know that that's going to be a percentage if you multiply by 100. All right? So something that grows by 12% per year gets increased by a factor of 1.12 every year. Got it? 100% plus 12%. Okay, good. Use the graphing calculator to determine how much the guitar is going to be worth now. Now, at 10:57 on a Monday morning. Now. Or what does it mean by now? We'll stick with year, 2024. Now, we need to come up with, first of all, the X value. He bought this thing in 2012. So how many years has it been since 2012? 12. So X is going to equal 12, not 2024. We're using 2012 as our T equals 0, if you will, or X equals 0. Okay, let's go to the calculator, Medora the Explorer, and put in the equation. We got Y equals 12 grand. 1, 2, 3, times 1.12 raised to the x power. Now, don't just hit graph. Don't just hit Zoom 6. We're going to come up with our own graphing window. Go to window. What are we measuring x in? What are the units of x? What are the units of x? Is it degrees Fahrenheit? What are the units of x? No. X is in years. Y is in dollars. Okay? So, what is a good lower and upper bound for years? Should we look at negative 10 years? That's 10 years before 2012. Should we do that? No. I'm going to put 0. You can even put negative 1 if you want to see the y-axis. We're starting in 2012. X max has to go out at least how far if we want to know what it is 12 years later? It's got to go out to 12. Let's go out to 20. Okay? That'll be 1932. That's coming up. That'll be before you know it. All right, let's go down to y. We're measuring dollars on the y-axis. There's a horizontal asymptote at 0. Should we look at negative 10? No, we can look at 0, but I'm also going to remember that the calculator uses the top and the bottom of the screen to write. So I know that 0 is a good lower bound. $0. That's if the guitar becomes worthless. I'm going to leave it at negative 10, so I have a little buffer. Y max, that's the maximum value of the guitar. He purchased it for 12 grand. The price is only going to increase, or its value is only going to increase. So what should we put for the Y max? We just kind of think of something that's reasonable. 20 grand, 20,000. I like it. 20, and then 1, 2, 3, and then you can leave your X scale and your Y scale to 1. That's just going to put marks everywhere. It doesn't matter. Hit graph. Whoa, whoa! This guitar is becoming more valuable than we thought, isn't it? We put our max at 20,000. It's already exiting the screen just a couple of years later. So we should go back and adjust our Y max to what? Let's try 50,000. This is a good investment. If you can get something that's guaranteed to increase by 12% per year, 50,000 is good, but it still exits the top of the screen. So we can do even better. Let's go back to 50,000 and change it to what? Let's be real hopeful here. 100,000, very good. Yeah, I'm going to go to 100,000. You can go to 75,000. I'm going to hope this guitar becomes worth $100,000. It is Gary Moore's after all, which was Peter Green's, which is now Kurt Hammett's. Does that look like a good graph? Did we think through the window reasonably? Yeah. So that's good. All right. So now it says, how much will the guitar be worth now? Since we have 12 in our graphing screen, you can either hit trace, type in a 12, and hit enter. Now here's what you have to show. Y of 12 equals 4675 point. How many decimals should we round to if we're talking about money? 2. So that's going to be 0.71. And I'll put a dollar sign in front. Or you could say dollars at the end. Man, I would love to have purchased that guitar for 12 grand to have it become 46 grand. It takes money to make money. It was an expensive guitar to begin with, but gee willikers. It's worth a lot more now. We've almost quadrupled its value. Okay. How do you get 12? You hit the trace button first. Hit the trace button, and it'll give you a little cursor, and then you just type in 12. Yeah. Now, remember how we did it with the other one? You could also go to the home screen. We're going to be using the home screen here in a bit. Go to the home screen and then do alpha trace number 1. Alpha trace number 1, remember, and that recalls Y1. And then you just put parentheses 12, close parentheses, and you can evaluate it from the home screen. So there's 2 ways, right? You should know how to do both ways. Y'all are honor students, right? Okay. Cool. Tony thinks about selling the guitar. Who wouldn't, right? Who wouldn't? But then he wonders how much the value would have increased by if he waits another 2 years to sell it. Well, we can figure that out right away, right? If he waits 2 more years, let's do it from the home screen this time. Alpha trace number what? 1. Alpha trace number 1. And now we're going to use what year if it's 2 years later from 2024? 14. No, 14. 12 plus 2 is what? 14. 58,000. Holy moly. That's another 12 grand. Okay, now, it didn't ask what the value of the guitar is going to be in 12 years, does it? It asks for the average rate of change over the 2-year period. And here's a hint. We found average rate of change lots of times. Average rate of change is the what? It's the slope of the line. It's the slope of the line. So here's what we're going to do. We're going to go ahead and say the average rate of change, and you can use ROC for rate of change. It's going to be the difference quotient. We've talked about this all year long. We do it for every function we study. It's the difference quotient. That's what we call it. It's going to be y sub 14 minus y sub 12. That's like f of 14 minus f of 12. Let me move this down. All over 14 minus 12. This is just your delta y over delta x from algebra 1. Y of 14 minus y of 12 over 14 minus 12. Now, here's the deal. I have y of 14 sitting right there, and I have y of 12 sitting right there. Do I want to use the rounded numbers to calculate my number, or is that just bad practice? It's bad practice, right? You don't want to use rounded numbers for a subsequent calculation because you get what's called compounded error. The error just keeps getting worse and worse and worse. So I want to be able to use all those values, which even the ones that aren't showing, the calculator is storing more decimals that it's not showing. So here's how we use our calculator. I write this down, and I show that I'm just doing change in y over change in x, but then I can type that directly into my calculator, just like that. Watch this. From the home screen, hit alpha x. That gives you your horizontal division bar, doesn't it? Now, in the numerator, let's put alpha trace number 1 of 14, close parentheses, minus alpha trace number 1 of 12, close parentheses, all over 14 minus 12. Does that look like the difference quotient on our paper? Yeah, it's why so it looks exactly like it for the most part, yeah? So now we just hit enter, and we get our answer. It's going to equal 5. Whoa, I'm writing with a highlighter. I haven't done that in a while, stupid highlighter. 5946.81 or 82, either one. Now, what are the units going to be? Dollars per year. Very good. If you look at this division bar, that's your quotient. The units of the numerator are dollars, and the numerator of the units of the denominator are years. So we read that horizontal division bar like a rate. We read it as the word per. So you have dollars per year, dollars per year. So I'm just going to go ahead and write dollars per year. On average, if we had to write a sentence, on average, that guitar over that 2-year span increased by almost $6,000 a year. That's half of what he paid for it per year. You get your money back pretty quickly. It is Gary Moore's guitar, after all, so you would expect it to increase rapidly. No one knew who Gary Moore was before you walked in today, but you're going to leave knowing who Gary Moore is. Some of you might even go to Spotify and listen to Parsinian Walkways, which is Gary Moore's biggest hit. And he'll hit a note towards the end of the song, and he'll sustain it for like 30 seconds, and you'll just feel the pain through the guitar string. And you'll be like, oh, Gary Moore, you hit me in the feels right there with just one guitar string. Gary Moore. Dollars per year, right? Okay, cool. Any questions on how to do that on the calculator without getting rounding error? It's simple, right? We use the calculator as a tool. All we have to do, all I ask of you is to show that highlighted piece right there. What's another name for that highlighted piece? What do we call it? The what? It's the average rate of change. It's called the difference quotient. It's the quotient of two things being subtracted, the difference quotient. All right. Next question. In what year will the value of a guitar be 50 grand? In what year will the value be 50 grand? Now, 50 grand is an X value or a Y value? It's a Y value. So I know that the Y value has to be 50 grand. So here's what I'm going to do. I'm not going to solve this algebraically. I already have this in Y1. I already got that in Y1. I'm going to graph this in Y2 and see where the two graphs do what? Intersect. Now, I do want to see this written down. I do want to see Y equals 50 grand. So now let's go to Y equals. We'll go to Y2. We'll type in 50 with 3 zeros at the end, 50 grand. We'll hit graph, and boom. You see a horizontal line? Well, there it is. Now, how do we find the point of intersection? Do you remember the keystrokes on the calculator? Not zoom. It's the trace. Second trace. Second trace is the calculate menu. Second trace is your calculate screen, and of course it's number 5. And remember, if there's only one point of intersection and there's only two curves, you can just hit enter 3 times. Enter, enter, enter. And it tells you right there that x, we want the x value, not the y value. So we say x equals 12 point, let's do 3 decimals here. 592. I like to truncate. You can round. 593 is fine. And then we'll put units on the end. He buys it for 12 grand. And in 12 and a half years about, it's worth 50 grand. That's a great investment. It's a great investment. You don't even have to be a guitar player to invest in a guitar like this. This is a money-making deal, right? It's good. It's better than having like Shohei Ohtani's rookie card or Wembayama's rookie card. They don't even increase that rapidly. But this is Gary Moore's guitar after all. You would expect it to increase rapidly. Yeah, Gary Moore after all. Does anyone here have a favorite guitarist? Do you even have a list? Like, I have a favorite guitar. David, who's your favorite guitarist? Who? Jimi Hendrix? Who doesn't like Jimi Hendrix? He was such an innovator. Oh, yeah, Yahweh Malmsteen. He's like speed fingers. Yeah, super speedy fingers, right? He picks his nose and you don't even know it. He's that fast with his fingers. They're like, whoop, I just picked my nose. You're like, holy moly. Malmsteen? Yeah, he's good too. I'm glad you listen to that kind of music. Today is Metal Monday, by the way. Or just Music Monday, right? Grateful Dead qualifies. All right, at the same time, he has also considered buying a brand new guitar for 18 grand. This guy's made of money that experts estimate would decrease in value by 1% per year. Why would you buy a guitar that's brand new if it's only going to devalue? Well, maybe you play guitar and maybe you need that new guitar for your band, right? And who cares if it's going to decrease by value by 1%? Someday you're going to become famous like Gary Moore, and then it's going to increase in value again, right? There are things that we buy that inevitably decrease in value every year, right? Can anyone think of something that's expensive that we buy that decreases in value? Are homes like that nowadays? Phones get more and more worthless as the technology improves. Cars is the big one that I was thinking. You buy a car and it wear and tear, baby, right? It just unless it becomes one of those classic vehicles, it devalues every year. Homes appreciate like the original guitar. All right, it's going to decrease in value by 1% per year. Determine after how many years the two guitars are going to be worth the same amount. All right, so what do I need to do first to determine when they're going to be the same amount? Do I need the equation for the second guitar? Yeah, so let's do it again. Let's do y equals, what's the initial amount of the second guitar? 18,000, so 18 with 3 zeros. Okay, now, what is the base going to be? It's going to be 100% of what it was the previous year, but now is it plus 1% or minus 1%? Minus 1%. And how do we represent 1% as a decimal? 0.01, okay, to the teeth power. Or we're sticking with x, sorry. So that becomes, if we simplify, 18 grand. What is 1 minus a penny? Yeah, so it becomes 0.99 to the x. So what the base does is it tells you how much you actually retain every year. We retain 99% of the value, but we lose 1%. Let's go ahead and list it here. What is the decay factor? Because it's getting smaller, we say decay factor. And what is the decay rate? Okay, who can tell me what the decay factor is? 0.99. The decay factor is just the base every time. The growth factor is the base. The decay factor is the base. We multiply by another 0.99, 0.99, 0.99 every year times 0.99. That's how much we retain. If we retain 99%, we lose 1%, which brings me to the decay rate. What's the decay rate? 1%, or if we list it as a decimal, 0.01. They mean the same thing. Okay? I like the percentage. And that's my percent symbol right there. I kind of slide it over like that. It kind of looks like a guy with a face, right? Kind of looks like a guy with a face who's looking at something with a pointy nose. but it's not. It's just my percent symbol. Okay. All right. Now, what do I do with this second equation? I go to y equals. I get rid of the 50 grand, clear it out, and I type in the new equation: 18 grand times 0.99 raised to the x power. My window should already be good, huh? Yeah. So I just hit graph. If your first window is good, your second window should be good. There you go. Now, how do I find where they intersect? Second trace number 5, 5, 5, 5. And then you hit enter, enter, enter 3 times, and you get x equals 3.286. I like to truncate. It says to round to the nearest tenth of a year. I'm always going to go 3 decimals by habit. That's the AP standard. If you're going to take AP Pre-Cal or AP Calculus or even AP Stat, it's 3 decimals. It does say to a tenth of the year. I guess I should follow instructions. So 3.2, or if you round, 3.3. So 3.3, and what are the units on X? Years. So you can put YRS. There you go. This is good analysis. We know what's happening with the guitarist now, right? So he buys one for 12. He buys another for 18 at the same time, let's say. And in 3 years, they're worth the same amount. That either says a lot for the one that's getting more valued, or it says a lot about the one that's losing its value, right? Like, you got gypped, dude. You got gypped. That $18,000 guitar, he doesn't even have strings on it, right? Oh, man, strings are extra? I didn't know that. I'm going to break the bank. What are strings, basically? Probably $5 a piece, $30. You can buy strings on Amazon for $30. Yeah. So maybe the guitar was really $18,030 if you throw in the strings. All right. Any questions about the first question? His name is Gary Moore, an English guitarist, my favorite of all time. Give him a listen if you like guitarists. All right, let's move on to then. What do we do when we have bass E? As I mentioned in the section on E, E is the natural bass. It shows up a lot in nature, so it makes sense to have exponential equations that have E in it. Okay. Now you're not going to have to write an equation with E in it. If you have E, you're going to be given the equation because it's a little more tricky to write the equation with E in it. You have to have some pre-cal skills using logs. Now, let's go ahead and review. Although the function e to the x has base e to the 2.718, we can write the e function as e to the cx power. Notice that, e to the cx power. So there is going to be a number in front of the x. When you're given the equation, there is going to be a number in front of the x. This is the same as e to the c to the x power, right? When you raise a power to a power, you multiply. So e to the cx is the same as e to the c all to the x power. Let's look at example 2. A paleontologist. Y'all know what a paleontologist does? Is that the person who collects stamps? No, that's a philatelist, by the way. The person that collects stamps is called a philatelist. I know y'all knew that. A paleontologist studies what? Bones, right. Yeah, bones. Your sister told you that. Uncovers a fossil of a saber-toothed cat in California. Woo! To live in California during the saber-tooth days, you had to be careful. The saber-toothed tiger can get you like a vampire. Probably kill you. The paleontologist analyzes the fossil and concludes that the specimen contains 15% of its original carbon-14. What the heck does carbon-14 mean? Have you heard of carbon-14 dating? Okay, there's something called carbon-14 dating, everybody, and it's what paleontologists and any archaeologists use to approximate the how old a once living object is. Okay, when they discover it. Here's how it works. Every living organism, whether it's plant, animal, or fungus or whatever, has carbon in it. Did y'all know that? Every living thing has carbon in it. The atomic number for carbon is 12. 12 is a very, 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 very stable number for carbon. In fact, carbon 12 is a stable element. There are radioactive isotopes of certain elements. An isotope is an element that has more electrons in it, okay? And they are radioactive, which means they shed their electrons, okay, to try to become stable. Everything that is affected by the sun, which is every living organism, right? Even vampires that stay indoors have to eat chicken, and chicken are affected by the sun because they eat grass, and grass grows by photosynthesis, which is affected by the sun. Got the idea? So every living animal that's affected by the sun, which is every living thing, it gets carbon 14. The sun causes the carbon 12 to become carbon 14, which is now a heavier atomic number. Carbon 14 is trying to become carbon 12 stable. So it's trying to shed its electrons. But it does so at this rate. It loses half of its mass. Anything that has carbon 14 in it loses half of its mass roughly every 6,000 years. Okay, so if you discovered a bone that had like 20 grams of carbon 14 in it, that means that every 6,000 years it loses half of its mass, half of its mass, half of its mass. That's exponential decay, right? So because we know how long it takes for carbon 12 to lose, or carbon 14 to lose half of its mass, we can decide how much carbon 14 is left in the specimen, what percentage is left, and we can compare that to the original amount of carbon 12 that's still in there, that's stable, and we can predict, right? All we're doing is we're comparing carbon 12 amounts to radioactive carbon 14 amounts. And we can see how old it is. It's a brilliant way to do it. So here's what this happens. The paleontologist concludes that there's 15% of the carbon 14 left. 15% of the original amount of carbon 12. And it can be modeled by this equation. There are ways to write this equation. Okay. I'm not going to get into the specifics, but you're handed this equation. So we're using N of T instead of Y. Is that okay? What could N possibly mean? Why N? Saber-toothed cat. Does that have an N in it? No. Carbon 14. Does that have an N in it? Carbon. There's an N at the end of carbon. Maybe that's what we're doing, right? So we're using N instead of Y. We're using T instead of X. That's okay too, right? Guess what 100 is? It didn't tell us what the initial amount was. It gave us a percentage. So when you're working with percentage amounts, it's always a good idea to start with 100 because 100 is 100%. That's what that means. We start with 100 grams or 100 pounds, whatever it is. And now we have e to the negative 0.00012 t. Okay? So when I look it up above, e to the c, t, means that this is e to the negative 0.00012 t, which means e to the c, if we isolate it, is e to the negative 0.0012. Okay, that's going to be important later. It's part of the form that you have to memorize right here. If we look at any exponential form that's base e, it's going to be e to some number times x. E to some number times x. And the number in front of the x is the c value. Now, usually we use c for a horizontal shift, and we use b for the horizontal dilation. I don't know why they're using c, but they are. It could be any variable. So c is just the number in front of the x in the exponent. Got it? So our e to the c is e to the negative 0.0012. You just get rid of the variable, and you have e to the c. That's why it's e to the c. It's part of the form. Okay. Does this function model exponential growth or exponential decay? Explain. Decay. Why? ¿Por qué? Ah, good. ¿Por qué? Decay. ¿Por qué? What's happening with the carbon 14? Is it building up? Less and less. Yeah. The carbon 14 is decaying, for lack of a better word, which means its amount, if you want to say this, its amount is decreasing over time. And we know how it decreases. That's how we came up with that number in front of the t in the exponent. That number comes from the half-life. Every 50, 59, 70 years, every 5,970 years approximately, carbon-14 loses half of its mass. Okay? You don't need to know that because the equation was given. All right. What is the initial value of the function? We already highlighted it. What is it? 100. Okay? And that basically means 100% of the original amount. When you're working with percentages, you can use 100 as your initial amount when you're dealing with percentages. Okay. Determine the age of the fossil if 15% of its original carbon-14 remains. Okay. So we're the archaeologists or the paleontologists now. We know that there's 15% of the original carbon-14 left. We know that we have an equation that we came up with. You don't need to know how, but we have the equation that was given to us. We can determine its age. All right. So here's what we need to do. Is 15% of its original carbon-14 equal to N or T or neither? Let's figure this out first. Let's answer this question. What is 15% of the initial amount, which is 100? What is 15% of 100? If it started originally with 100, we just answered that in the question above, and now there's 15% left. What's 15% of 100? Don't think too hard. It rhymes with 15 and starts with F. 15. That's why we start with 100. It's super easy if we start with 100. What's 30% of 100? 30. What's 98% of 100? 98. See how it works? It's easy. All right. So we want to know now when n of t, when the amount is equal to 15. We want to know when y is equal to 15. Okay? So here we go. We're going to set n of t equal to 15. So let's go to the calculator. And we'll type our equation in y1. We haven't even done that yet because we've been thinking. All right, so let's type this in. 100. Now, how do we get e to the power of? The easiest way is to hit second ln. Second ln is the blue feature, the second feature, and it's e to the, it already gives you the exponent. Second ln. Second's on the left side, ln is to the left of 4. Okay, now we can type in negative 0.00012, and instead of t, we use x. All right, now in y2, we're going to put what? We want to know when it's equal to what? 15. Now, don't just hit graph. We need to go to our window and think about a reasonable window. What are we measuring on the x-axis? We're measuring time in years, right? And what are we measuring on the y-axis? Amount of carbon-14, C14. It could be measured in grams, probably, micrograms, whatever. So what would be a good lower bound for years? Do we need to go negative? Did we discover it before we discovered it in negative land? No, so 0 is a good left bound. What's a good upper bound? How old do you think this fossil can be? This is the one you have to kind of play with. 1,000. Let's try 1,000. Let's try 1,000 years old. Okay. All right. Now for your y min, this is the amount of carbon-14 left. You can put negative 10 because we know 0 is the low point, right? And what do we know for sure is the high point? What did it start with? It started with 100. Is it going to get bigger than 100 or smaller than 100? It's only going to get smaller than 100. So if I put like 120, which gives me a little bit of buffer, that should be good, or even 110. I really could go from 0 to 100 there. All right, let's hit graph and see what we see. Whoa, I see both curves, but it appears that the blue one's going down so slowly that it's not going to intersect the red one for a little while longer, yes? So that just means we need to look a little bit further than 1,000 years. So instead of 1,000, let's go out to what? Let's just do by a factor of 10. That's a good kind of strategy. Let's just put another 0 at the end and go out to 10,000. What do you say? You want to try it? All right, let's try it. Oh, boy, boy, boy. We're getting closer, aren't we? Let's go to our window and go to X max. Let's do another factor of 10. Instead of 10,000, let's go 100,000 years. 100,000 years. Hit graph. Did that do it? All right. So in general, you can go out by a factor of 10. Start with 10 years, 100 years, 1,000 years, 10,000, whatever. Now I can hit second trace number 5, enter, 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 and I get t. I'll put t this time instead of x. I get t equals 15,809.333, and then what are the units? Years. Isn't that amazing that you can find a piece of bone and with just a little bit of chemistry, biology, and mathematics, you can determine that the thing you're holding in your hand is almost 16,000 years old. That's amazing. To me, that's amazing. And that's the power of math. Valerie, do you need help?
Yeah.
Let me see your calculator.
Mine looks weird too.
What? What? Oh, you have 100.
Well, I wrote it down. I think.
Did you do second ln?
Yeah.
Here, type it in again. You type in 100. Here's what you type in: 100 second ln, which brings you e to the power of, and then very carefully you type in a negative. You don't need the leading zero if you don't want. So at least you put negative 0.00012, and you need the x there. If you forget to put the x, you're just going to get another horizontal line. And then in y2 you put 15. Okay? Syntax. Let me see. I think you're putting the minus. Yeah, you're putting. Okay, so because it's here's what you do. This is a very important thing. You need to put a negative symbol instead of a minus sign. Okay.
But we are having a meeting with seniors during advisory.
Use the negative sign instead of the minus sign, and it'll work. Okay. All right. We'll stop right there. Obviously, we'll pick back up with this tomorrow.
For a short presentation that we're going to go over, but again.